if you solve for zeros of that function, you can find places where the things would change.
You could solve for the root. I think that's what you're saying.
Yeah.
Are there going to be roots for a Levenspiel plot? Is there any time where the...
No, I'm saying of that function itself, so you know where things like slopes would change.
Right,
So,
but I'm saying, are there going to be meaningful roots for this problem?
Then our root's called the derivative.
Yes. That's the next strategy that you want to employ. Right? Is rather than solving for roots, what if I solve for extrema? Right? Levenspiel plots might go through maxima or minima. You guys have seen that on your homeworks. The phrasing of the question might have given it away too. But, yeah, so how do I do that? How do I solve for an extrema? So the derivative of k minus k over Ra with respect to what?
X.
Big X, yeah, conversion. And what's that equal to? Look at that. Without a calculator and everything. I didn't even have to go to Wolfram Alpha. So when is this equal to 0? So this slope is equal to 0 when? 0.1, right? I move that over, it becomes positive 1, 1 over 10, 0.1. All right, so now I have a third point, 0.1. And I could go back and plug that into this equation. And so what do we get if I do that?
19 over 500.
Seriously? I mean, I believe you, but...
Did you have to do that?
Yeah, what I get is 0.95. I don't think that's 19 over 500.
Just forget it.
Yeah. 0.95. All right, so I have 3 points. Are they straight lines or curved lines? Curved, right? This is a quadratic. So don't forget all of high school math when you become seniors in chemical engineering. Wait until you graduate first.
Did you have to do the derivative point? Or could you
It's
just
a,
take-
Yes.
it's a really
You had to
necessary
do the
point
derivative.
to.
To solve the problem, yes. Because think about the next part of this problem. Now I've got my Levenspiel plot. So, what conversion do I want to get to? I've always been jealous of the people with colored chalk. Because this would be the perfect time to use it, right? All right, so that's where I want to get. So what arrangement of reactors should I use? Now explain your reasoning. Area under the curve. So at what point do I want to start to switch to the PFR?
At point 1.
So the thing to keep in mind is that if the Levenspiel plot is increasing, use a PFR. Because the area under the curve is going to be smaller than a rectangle. If the Levenspiel plot is decreasing, what do I want to use instead? CSTR, because now I just get a rectangle. So some of you might have caught on as soon as the problem was phrased, right? That there's probably going to be a minimum point in this quadratic that you've been given. It's not like the most shocking thing in the world. That we had some second order function, we ended up with a quadratic, and sure enough, we have a meaningful minimum point. Okay, so we want to go CSTR to PFR. Looking back at it, it actually doesn't ask for the volume. If it did, could I give it the volume?
Yeah.
Those pumps.
Yeah, we need the flow rates.
You need flow rates. What else do you need? You need
K.
K. K is not something you should ever estimate. I heard a lot of people saying estimate K when we started this problem. Let me just put that as an always true. Never estimate rate constants.
Well, I mean, when I said that, I meant it just scales.
It's
your
not a criticism. It's just saying. I understand. I understand. It's not criticism. You're right. You could have used a basis, right? A lot of times people will say that, use a basis, and that. But you get to the same answer by just leaving K in there. I mean, because in some sense we kind of did treat it as if it were 1 by just moving it over. Okay. So yeah, we want to use a CSTR that has an outlet conversion of what? Should the CSTR outlet conversion be? 0.1. So I could have asked you that. I could have asked, what is the outlet conversion of the first reactor? I wouldn't have told you the CSTR because that would have just been a gimme, right? But I could have asked you what was the outlet conversion of the first unit. And that way you'd actually have to solve for this midpoint rather than simply recognizing that it was going to be an upward shaped parabola, at which point you could have already said PFR goes to CSTR. Other way around. CSTR goes to PFR. All right, part B. It says, it has been found that reaction conditions must be carefully monitored and controlled to maximize selectivity. What type of unit would I want to use in that scenario? Say it loud and proud. CSTR, right? Because CSTRs operate at one condition. They don't operate over a range of conditions like a PFR does. So if I want really tight control on the conditions that are present within my reactor, I'd use a CSTR. Plus, they're well mixed. Yeah. Sure. I hadn't even finished the question yet. We'll get there. It has been found that the reaction conditions must be carefully monitored and controlled to maximize the selectivity, and therefore CSTRs are your only option. Using 3 CSTRs, determine the fractional conversion that must be achieved when the products leave the first and second stages. Again, with the caveat that you want to minimize your volume. So, what's the conversion here? Say it louder. And I've got 3 CSTRs. And it's asking me for X1, meaning the conversion leaving reactor 1, and X2, meaning the conversion leaving reactor 2, and X3 is equal to 0.8. But one of them we know real easily. Yeah, we know the first one. It's going to be the same as the first problem. Nothing changes now that I'm using 3 CSTRs. My first CSTR is still going to be sized so that it stops at this minimum conversion. All right. So this is the one that actually requires some work.
How are we defining conversions again? Because if X3 is 0.8, that's the overall conversion.
Yeah, X3 is also equal to that. The conversions have been defined, and somebody correct me if I'm wrong, but I thought that they were defined by simply what the conversion of the exit stream is relative to the first stream in the series of reactors. I'm pretty sure that's how the book and all the homeworks have done it. So it's not the conversion within the third reactor. It's saying when you're leaving the third reactor, you're at an 80% overall conversion.
He uses both sometimes in the textbook though, but he usually distinguishes like what
Well,
he's talking
yeah,
about.
at least hopefully he distinguishes, yeah.
And we're saying that the first CSTR, the conversion stops at 0.1. That's because according to the plot, we have that dip, and that's why we don't have to find it again.
Yeah. Yeah, it's because that's the minimum point on my Levensspiel plot. So just like when I was able to use a PFR, I was going to use a CSTR with an exit conversion of 0.1. Now that I can use, so this problem is really, how do I replace the PFR from part 1 with 2 CSTRs in order to minimize conversion? Because it's the same, I wouldn't ask that because that would give away the answer to part A, right?
Are they of equal volume? Or
No, you have to tell me. That's the whole point of the problem. If they're of equal volume, then it's a little bit easier, right? So the problem statement said, your goal is to design a flow process to achieve a fractional conversion of 0.8 with the minimum total reactor volume. That's for all three parts. That wasn't inside part A. That's just in the problem statement. Okay, so what do I do? What am I trying to minimize? Volume. Which volume?
Total volume.
What is the volume equal to?
Volume 1 plus 1.
Let's start small. Has volume 1 been determined? Yeah.
Can you do this problem by taking it and instead of thinking about it, just think about it as you want to minimize the area for the detergent and broke it up into rectangles?
Yeah, that's what we're going to do.
I just,
No, I mean, that's literally what we're about to do. Okay, so V total is equal to all three of these. Have we already determined that one of the volumes is going to be some value?
yeah, we don't.
Right, so this one has been set already. And so really we want to minimize the sum of the second two reactors. That's the only thing that's left to be determined for this problem, is what is the volume of the second two reactors.
How do you know V1? I know it's something to do with the area.
You don't numerically know it, but it's set. That's the point, is it's set. I've already determined that its exit conversion is going to be 0.1, so I can't change its volume at this stage. Okay, so what is V2 plus V3 equal to?